Hello, everybody, and welcome to Low Pressure Area, a new podcast from Campbell Scientific. This is a podcast where we're going to explore everything to do with the weather, meteorology, answer some of those questions about things that you've always wondered about when you look outside in the morning, but never really knew what the answers were previously. We're going to look at how certain parameters are measured, some of the challenges we have with measuring things, and then maybe what they do impacting climate in the future as well. My name is Jamie McDonald. I'm the marketing manager for the environmental division at Campbell Scientific here in Europe. And joining me today, and hopefully for many episodes into the future too, is my colleague Richard. Richard, over to you.
Hi, Jamie. So Richard McKay, I'm a Canadian living in the United Kingdom, also in the European area. As part of our environmental division, I'm a product manager for a lot of our products, mostly the remote sensing optical products. Worked in the public domain with Canadian Meteorological Service for a number of years, and then moved over to private industry through a number of companies. So hopefully I have a broad breadth to have these discussions with both you, Jamie, and the audience, but equally we'll have some other hosts as well to share that around a bit and where expertise brings in some other skill sets. So looking forward to it. Thanks.
Yeah, absolutely. And I think, as you say, that background that you've got is really impressive, and one of the reasons why we wanted to start this to begin with. I think it's fair to say that you're a bit of a Met guru in that sense, and you bring a lot of knowledge to the colleagues that we've got in the office here, and it's something that we'd love to share with a wider audience as well. So this podcast is something new from Campbell Scientific, and we really want to use it as an opportunity to share some of our knowledge with a wider audience. And as I said, answer those questions that maybe you've always had in your head, but never really got the answers to. Christmas is a time of year when we often talk about weather forecasts, particularly in the Northern Hemisphere, because everyone's asking, is it going to be a white Christmas? Are we going to have snow on the ground to have that full Christmas feeling? Now, Richard, you'd worked with another colleague of ours here in Europe to put together your own forecasts to see whether we were going to have a white Christmas in our office locations around the world. And I think this is always a fun thing to do because we never really know whether they're going to be true or not, even though I know you leave it till a couple of days before with the hope that it will be as accurate as possible. The question really that we're going to look at today then is, how difficult is it to make those forecasts? How did it go for you? And why is it difficult for forecasting generally? What are those challenges and how do we solve them?
Yeah, it's a great topic to start this off, Jamie, and hopefully one that piques the interest of a number of our audience members. And some might be experts in this field, and obviously, to cover this topic in the time that we have allocated, it'll be fairly general, but we can always look to dive into specific aspects in more detail in future podcasts or episodes. I guess the challenge with trying to forecast the weather, whether it be Christmas or whatever the weather is outside, typically it comes down to that it's an inexact science, meteorology, and there are only theories. There aren't yet laws that dominate how the atmosphere and the interaction works. And so it's a chaotic system, and a chaotic system by nature means that if you had a known set of variables and you knew the values of those variables, so temperature, wind, humidity, cloud, solar incoming radiation, excuse me, and other parameters that are usually affecting the weather, and you ran them side by side, you would get two different outputs. And what it sometimes comes down to is the decimal place. So basically whether the temperature is to 3 digits or 4 digits and how accurate that measurement is. And it sounds incredible, but the smallest details can make a significant change. And that's part of the challenge. There are others, of course, but that really having good spatial coverage of data over our planet, much of it is water, so roughly about 70%, and very data sparse. So, we try to use satellites and other tools to help us in those regions. But equally, even where we are on land or close to the coastlines, you can have data, but sometimes just how good that data is. And again, a challenge of trying to measure out on, the ocean and deal with contamination and other factors, and just power and getting the data back to where you are can be a challenge as well. So if you have no data, it's certainly a lot worse than having some data that's maybe a slightly lower resolution. So there's many different challenges, but coming back to the question about Christmas, and particularly because it's been a recent topical event, we didn't have a white Christmas in the United Kingdom. Certainly, I should rephrase that. Maybe in England, Scotland certainly had a number of snow events, and I believe even our Paris office had some snow, but it might have just been some flurries more than any snow that was pitching on the ground. And some places that would typically have expected to have snow in North America, our Edmonton or the Logan office in Utah, I think those again were abnormally, let's say, warmer and milder than they would have been in the past. And so, although I think maybe in Edmonton there might have been snow, it wasn't. It was already on the ground. Didn't snow on the day per se. So, and again, it comes down to the question of, do you define is it a white Christmas as in it's going to be snowing on the day, or is it actually on the ground already? And there are different ways to interpret that. I won't go into that in this topic, but yeah, just it's one of those points. So we put it out for, I think, 14 different office locations around the globe. And that was from Brazil over to Japan to the Finland office, where some people are located. Interestingly, the range of parameters was from, I believe, something in the mid 30s temperature Celsius down to minus 30 or minus 40 in the Edmonton office. So there was a huge variation, and part of that challenge is that to forecast the weather, we use something called numerical weather prediction, and a number of tools that go along with that. And I'll show some slides in a minute or two to talk about that. But typically, there's only a couple of global models that are used, and that have sort of a provenance to them, and a large base that's fed into that to make them better. So the one we were using was actually based on the German Weather Services model that they're using. There are a couple of others. For example, the UK Met Office has one, and there's certainly one that's used in North America quite prevalently, and of course others use those models interchangeably. But so there's a handful of models that are used, and some of them have better, I'll call it, skill in certain areas or types of conditions, and others will have other specialities, and each, of course, has some weaknesses. But to maybe just help with this discussion a bit, I'll jump over and share my screen here quickly. And we're not going to do PowerPoint death for anybody, but just to help visualize this a bit. If they can't see the screen, then obviously I'll still describe it and explain what we're talking about. But the numerical weather prediction models, they basically try to say, how do you divide the world up into a manageable sort of size? And that's by making a number of cubes. So you would, initially, those cubes could have been a quite coarse resolution, something in the order of, I'm going to say, let's say 100 kilometers by 100 kilometers by 100 kilometers. And I'll use metric as sort of, hopefully this will be a global sort of podcast, but for our imperial friends, then may need to convert some of these things. But you would basically try to do that for the whole Earth. And in the image that you'll see on the screen, then that does try to show that, sort of dividing it up into thousands of different blocks that are this kind of resolution. And then you would have to stack that vertically as well up into the atmosphere, because our atmosphere isn't just one block height of 100 kilometers. It actually, the breathable atmosphere is only as deep as what's known as the troposphere, and we sort of measure up to the tropopause. There are certain things that look at the layers above that, but basically that's where the moisture and oxygen really that we need is, and determines a lot of our weather. So that can be as high as 18 kilometers, which was recently determined that it could be higher than previously thought, where it used to be determined that it was around 16 kilometers. But the explosion that happened around this time last year in the one volcano caused some measurements that allowed us to measure that one up into the stratosphere and, as high as 18 kilometers in that particular region at that time. And it can be as low as 9 kilometers or even sometimes lower than that over the poles, just simply how warm the air is and therefore how high they are at the different times and what seasonal period you're in. But nevertheless, you're having to do this three-dimensional sort of cube stacking in all these domains, and you would try to do it for the whole globe. And you can imagine that even with the best supercomputer, it would struggle with that. And then, especially if you want to get to a finer scale resolution than 100 kilometers by 100 kilometers by maybe 1 kilometer height, you would then try to say, can I get down to 1 kilometer by 1 kilometer, or even finer than that resolution? And they're able to do that now. But what I'll say we as a community and involving ourselves as part of that, feeding into it with our observations and our systems, what we try to do is say, where's the area of most interest? So, for example, in Europe, I would say that predominantly the weather moves west to east. So you would typically be looking at the coastlines and monitoring how the weather comes across. And then when it hits land, it usually gets modified. And that's where you would want to measure, because most of the time, if there's no local influence or modifier to the weather, then it will carry on as it is. But if you introduce a source of moisture, or a lack of one, or if you change the temperature significantly up or down, or if you move it orographically up or down in the atmosphere by a mountain, or these kinds of things, or it starts to subside on the other side of the mountain range, then you modify it enough and it can change the weather. So you're looking at areas of interest, usually coastlines, and again, also because there's more data points there than maybe out on the ocean. So when it hits land, you want to have as much resolution and as much ability to look at that in detail as you can. And then as it moves inland, before you would have had to accept that same resolution everywhere, but now we can actually say, in the southwest, for example, of the United Kingdom, we want to look at that at 1 kilometer by 1 kilometer. And then as you go inland, you might have a coarser resolution where you could say, I only need to see it in 5 kilometer by 5 kilometer, or, 10 kilometer by 10 kilometer sort of resolution. And that allows you to save some processing power and other things that go along with this. But so you're trying to look at the area of interest based on the current conditions and then model that as finely as you can. And on the screen, we're showing a number of different interactions that happen there, like I was mentioning, whether that's solar radiation, the moisture in the atmosphere, the cloud cover, where the winds are going, the temperature, and different sort of other physical elements, like the way that the atmosphere moves and the dynamics of the atmosphere as it's going through there. And you would put in these parameters and then let the model run those, and it would come out with a, let's call it a forecast. And you want to know how good do you think that's going to be. And one way to check that is, because of this condition we were talking about, where you have it's a chaotic system and it depends on the accuracy of the measurements that you're putting in, and because it's challenging to go out and take a snapshot of the atmosphere at any point in time, because it is a real world 3-dimensional moving sphere, it's very hard to control that. So you're trying to get as best a measurement as you can. Then what you're doing is you typically try to model the conditions that could be associated with it. And what I mean by that is now this next slide that I'm trying to show, and that's showing something called Ensemble forecasting, and it's one of the tools that's used to try to help this. And you try to say, how sensitive is this model or the run that I'm trying to do for this particular area to, for example, temperature or wind or other parameters. And if I varied those, for example, wind, if I vary that by, either 0.1 of a knot or a meter per second, or if I vary it by 1, meter per second or knot, how much would it change what's going to happen to my forecast? And typically you would run something like 1,000 or several hundred iterations of this by varying these values, and then try to see, is there good agreement, basically? So, on the slide deck, I'm trying to show that generally there's good agreement initially, because there isn't as much room for the change to happen. But as you go with increasing time, you see much more variability. And typically where we are right now, a long-winded way to say an answer of usually around 4 days or even possibly 5 days from now, you could have a 70 to 85% accuracy on the forecast. Beyond that, it's really challenging because the small errors become really significant with time. And that's somewhat what I'm trying to show on this graph, is that if you look on the left-hand side, it's showing that the lines are fairly close together, wherever that starting state is, because you're only varying it by a viewpoints on each side. But as you go with increasing time on the one axis, then the horizontal axis, then you are seeing over 4 or 5 days that there could be significant variance of, 200-300% or more from one value to another. And that's where you really have less confidence in what's going to happen, because you maybe don't have exactly all those parameters exactly right, and all of those differences add up to make a big difference. So,
and is it then fair to say, Richard, at this point, that when you're trying to get a more accurate forecast, then the more measurements you have and the more accurate or kind of precise that they are down to those decimal places can make a big difference to whether the forecast is accurate further out than those 3, 4, 5 days that you spoke about?
I think it's certainly going to help. There's a number of different points, and could be a topic for future discussion about how many data points do you need and how accurate do things need to be. Mm-hmm. But certainly more data points in data sparse regions will help, so that they give you more confidence and see the small changes happening quicker. And then more accuracy, or better accuracy should be better said, will ensure that there's less variability and better, let's say that 4 to 10 day period could be more accurate if you had a better accuracy. So 2 decimal places to 2% error instead of maybe 5% error or something like this. So right. that can certainly help. But a challenge with a lot of measurements is, even when you make a measurement, are you actually unduly influencing the measurement by being in that space? And how do you address that? And so that'll be a topic for the future, as well as how, for example, with temperature, how do we measure temperature, and how can that be improved, and what are some of the vagaries associated with that? But the good news is, really it was, I think, from, let's call it the 1920s onwards, that there was some really nice ideas about how to try to do modeling, how to try to improve weather forecasting instead of just what you could see out your window. And data collection was really a big challenge in periods before that. And we have records going back, several hundred years, and use other things, ice cores and other samples to try to get records from previous to that time. But really the data period that we have in good resolution is still somewhat limited, and then this modeling idea, the technology improvements and the ability to have computers help do that, has helped enormously to improve the forecast. So I believe it was something like 30 years ago, we only had sort of that 70 to 85% confidence in what the weather would be for one day, so 24 hours in advance. And then beyond that, it went down significantly. But now, 30 years later, we can have that confidence out to at least 4 days, if not sort of 5 days. And that certainly then goes down as you go out with increasing time. But again, that challenge of a chaotic system, and if you roughly have the same values, so 24.75 degrees Celsius temperature starting point, whether that's 74.39 or 74.82 can make a difference in that 5 or 6 day period. And that's where we need to have better coverage, but also better data accuracy in the measurements themselves, and a better representativeness of the measurement and measuring the parameter itself, maybe rather than some other approaches that are done. And that's just an example. So in a way, it's sort of like, how long is a piece of string? The more you pull it, there's more detail to look at. But things are improving all the time, and there's awareness of all the issues, and they're trying to address those piecemeal by different communities and groups around the world. And it's great to be part of a team that helps to address that. But to come back to the question, I guess, and maybe wrap up slowly here, is to say, we didn't get it quite right. We'd forecasted it would be snowing in the United Kingdom, and that the Paris office would see some snow. I think the rest of the offices, we were pretty accurate. Grant you, they weren't necessarily saying that there would be snow, or there was already snow on the ground. So I think it's those conditions where some of the subtleties in the way that the air, its position, and how much moisture was in it, wasn't enough to create just that thickness of cloud that would then produce some snow over the United Kingdom, for example. Didn't quite happen. Whereas in Paris, I think it just got that subtle thickness that it needed to give a few flurries, but it didn't really, pitch and stay on the ground. But that's part of the exciting bit is, it's an area of developing science, and great to be a part of that, and what gets me out of bed in the morning. So hopefully this has been of interest, and I appreciate people, joining in and looking at some of my crazy slides and drawings, but sometimes they'll be more professional than other times. And hopefully the descriptions help to explain some of those conditions when people can't see the images as well. So I hope that answers the initial question. Like I said, look forward to a lot of different topics, and even just some other completely different fields, but still meteorological or impacting us as humans on the planet, and how do we improve the lives of people.
Yeah, absolutely. And I think it's fair to say that your forecast, at least from my perspective, was rather accurate. I'm based here in Helsinki in Finland, and we're one of those places where you'd expect it to be a white Christmas fairly often. But this year your forecast predicted a green Christmas, and it was unfortunately correct. And it's a sign of the changing times, I suppose. This was really interesting, though, Richard, to see how it's done right now, and of course how quickly those forecasts models are improving. So obviously I'll be expecting next year for your Christmas forecast to be 10 days out rather than the 3 or 4 days it was this year.
It's an interesting last point I hadn't addressed yet, Jamie. Just appreciate this is going on, but just a last point that 2 years ago we only did it 3 days out to give ourselves a bit more confidence, and the problem with that, of course, was that it was that week where Christmas was in, and of course a lot of colleagues and other people that were interested had already gone on annual leave or planned time off. So this year we made the jump to say let's do it 7 days out, and of course 7 days out is where I was telling you in sort of this danger domain beyond the 4 or 5 days. So it added an extra spicy element to it, and like you say, some places it did well. The German model really is quite good, and did a great job in this particular instance. But like you said, I should give a lot of credit to my colleague Frank, who did a lot of the work, but I was helping to disseminate it more than anything. But yeah, it was an interesting experiment to go from a 3-day out to a 7-day out, and we'll look to try to maybe do that again this coming year, and 7 days out, and see where and how that compares, and maybe we can see in a year's time if we look at that and understand has any improvement been made, and how much of a marker have we set in the sand to show that. So yeah, good point.
Yeah, exactly. Well, I think this is probably a good time for us to wrap up, and thank you for giving all of your knowledge today, and teaching me certainly much more about how forecasts are made, and the interesting things that we need to look at to ensure their accuracy in the future as well as today. For our next episode, we're going to be taking a slightly different direction, though obviously still focusing on all things weather and meteorology, and looking at clouds. So, all of us look out the window in the morning. We probably have a quick glance up at the sky to see what it looks like, whether it's clear or not. I don't know about you, but more often than not here, there's some sort of cloud in the sky. So join us again for our next episode to hear about clouds, how they're formed, and the effects that they have on us and the weather systems around them, and much more on Low Pressure Area.